So, talking about a few things. I'm going to talk a bit about Markdown and note-taking in general for things like the DSI, especially for the DSI. But, Markdown is a great way to take notes in a number of spaces. I'm going to talk a little bit about Jupyter Notebooks, but mainly I'm just going to be using a Jupyter Notebook. I'm going to be running a Jupyter Notebook within VS Code, which you can do. There's I don't know if it's a Jupyter Notebook extension. I think it might actually be native to VS Code now if you have Anaconda installed. Actually, maybe even if you don't have Anaconda installed, I think VS Code is actually just now supporting that. So you can create a Python notebook, just create it or download it and open it directly with VS Code and use that Jupyter Notebook within VS Code, which is really nice. If you've used Jupyter Notebooks before, it's really nice to be able to use it within VS Code. You can also use them within Google Colabs. And then we'll talk about kind of what is machine learning, right? Because this class it's really about the basics of Python and applying Python to stats. Machine learning kind of came out of stats, and it definitely came out of stats, and it's kind of mysterious what it is, and I want to maybe get rid of some of that mystery if I can. It's still amazing, but the mystery around it is we can nullify some of that through maybe some simple visualization of how to abstractly conceptualize what machine learning is. And then we'll do just an actual workflow where we go through the steps that you would take on kind of any project. It'll be a simplified workflow, but it'll still be very much, kind of the standard that you will see in the DSI and elsewhere. Okay, so let's talk about Markdown. So you may not realize it, or maybe you do. I've been using Markdown this whole time. All these slides are written in Markdown. Now, they're not, super beautiful and amazing and all that. They're not like, I can't do a whole lot out of the box with Markdown to beautify it, right? But what I can do is have a very simple method of putting mathematical formulae and putting code and having different sizes of text within a document. And the READMEs on GitHub, those are all written in Markdown. I'm just going to recommend that you start using Markdown to take notes. And I'll try to give you a little bit of an example of what that might look like. So maybe I'll make a new document here. So I'm just calling this markdown example.md, and I just opened it here. So if I just write some stuff in Markdown, I'll just write this is Markdown. Notice I've got this hash right here. This hash is going to make kind of a larger. It's like a H1 in if you know HTML. It's just a big blown up piece of text, and I can actually preview this in VS Code, which is nice. I'll split this to the right, and we can maybe see how this renders. So this is Markdown, and then this is a smaller header. We can do this is yet smaller. Right, and I could keep doing this. I think it goes up to 5. This is smaller yet. And this is the smallest. And then I can bullet point these, right? So I can say bullet point. Another point. And notice that it formats it, and it's really kind of nice and simple. If I want to make kind of a break line, I can do this, right? That gives me kind of that HR, line. So the way that I've been making slides is, well, I put in a bunch of break tags from HTML to separate the slides, right? So there is a little bit of flexibility with this. In fact, you can fully utilize HTML in here if you want to, if you really want to make this, nice and slick and look really nice. But part of the reasoning around Markdown is that this is readable text over here, right? You can look at a Markdown file, even if it's in its raw text format, not in this nicer rendered format, and it's still readable. So, it's a very transportable kind of document. You can also put code cells in here, and I use these triple ticks, right? Kind of like what we do in Slack. And I can say, this is some Python, and say for I in range 20, print I squared, right? So I have this nice presentation over here. The code will be saving to GitHub in real time, or it should be. Let me just make sure. I may not actually have a cron process running here. Hold on. Okay. It definitely is now. I think I do have a terminal somewhere that is going to GitHub, but anyway. So this is nice because I can copy it and paste it into a text editor, right, directly from my notes, and it's not going to have any special characters or anything like that. It's also readable, and it has code highlighting. There's just a lot of really nice things about it, and there's support for a bunch of different languages, right? I think that's the way I probably want to do that. So for SQL, select star from, let's just do some table, right? So we can do this, we can do Java, we can do C, we can do, any language where there's support in Markdown, and that's most languages. And if you don't explicitly put a language in, you can have a kind of a nice separated box, right? So this text, looks, what is that? Looks like a system font, right? Or more like a system font. It isn't actually here, but it does render as a system font in other places. So in my attempt to sell you on Markdown for taking notes, really the thing that puts it over is support for something called MathJax, okay? So MathJax is based on, well, it's a sort of subset of LaTeX, which you probably, most of you will probably know as LaTeX. Only nerds pronounce it LaTeX, but that's how it's pronounced. So I don't know. Anyway, so this is MathJax is a subset of LaTeX that is supported in Markdown, right? And what that means for us is that we can embed mathematical formulas in here, right? So let's do I don't know, Cosine, do this. So we'll call this Poisson. And we'll assume this is the PMF of so this is going to be e to the negative lambda, lambda, multiplied by there we go. So let's do lambda comma k. So this is so far e to the negative lambda multiplied by lambda to the k over k factorial. So I can make this look a little nicer. I can actually, if I'm here, I might as well do this. So we have, a nice rendering of the formula here. I usually don't use times. I usually do c dot. Just that's the notation I use. But I just want to, point this out that this is really nice because you can take something like that and you can go directly to, in your notes, you can have a reference for the formula. And then you can also write the Poisson PMF right here, right? Lambda and k, and return, from math, import e, return e to the negative lambda multiplied by lambda to the k over factorial of k. So import also factorial. So yeah, I don't know if I've sold the benefit of this, but when you're in something like the DSI, and I say something like the DSI because maybe you're starting, let's imagine a different scenario. Let's imagine that you start as a developer at a company and they're training you in a new language. They're training you on a bunch of technology. How do you keep track? How do you keep track of everything that you're doing? This is going to sound unorganized, but what I recommend people do for things like boot camps or like 3 to 6 month training periods at jobs, I recommend that they make a single Markdown document that they can then Command F in, or Control F, depending on your operating system. If I'm looking at this and I'm like, well, Poisson, okay, well, this takes me directly to Poisson. And, mind you, this document might grow to be, 4,000 lines or something over time. You can, as you use it, as you reference it, you'll probably notice that, I know this thing that's in here. I don't need that anymore, and you can delete it out of there. You can also put links in here, right? So why don't we do that? So maybe I'll just call this example Poisson, and I'll link out to the Wikipedia article. So I'll say wiki on Poisson, and do I have, I don't actually have a browser open. Sorry, one sec. And I'll go Poisson. So I've got the Poisson distribution here from Wikipedia, and now I have a link to the article that's right there. If I click on that, it's going to open it up in a browser. So all of this gets saved in a nice way to GitHub. And why don't I find that? So what, that's January 19, source stats. And this is under this. So notice this all looks nice. One of the biggest things that gets you hired, really, just out in the world, is your GitHub. what does your GitHub look like? What's on it? How well have you maintained it? What are your significant projects? And, you know, like anything like that, how your project is annotated, how you write about your project is profoundly important. So this is all jumbled up right here, but, you know, I could take a little more time and space these out, format them a little nicer. But at the end of the day, this is very readable, right? It's not a wall of code, and I've got some embedded formula in here. I've also got links in here to other things. So, you know, one of the things I did in the DSI is I made a single README document, and I had that sitting at the, you know, just the landing page of a repository. I used a private repository because there were things that I put on there that I didn't that were proprietary, right? So I didn't want to expose them. But that's how, you know, some question would come up on an assessment, or I would need a quick reference. I would just, you know, Command F in you know, in my browser to find it. And if I couldn't find it in my own notes, I would, you know, Google it, right? If it was something I didn't know off the top of my head. So that's my sales pitch for Markdown. I really think it's a good place to, you know, to put some time and energy, and there's a very small learning curve on it. So, you know, the little bit that you learn there can help you just have better documents, better note-taking in general. And if you want sort of a reference guide for some of this, for taking notes, for things like MathJax, I've got, like, on our README, there's a couple links. Like, there's a link to a massive set of instructions in MathJax on Stack Overflow. It's really, really helpful. I look at it probably every day. The other thing, all the slides are in Markdown. So if you see something that you're like, well, I want to format something that looks like that in the slides, all of that is in, all those slides are written in Markdown. So you can just look at them with the text editor and get a good sense of how Markdown works. Okay, so the reason another reason I talk about Markdown here is here I've got this Jupyter notebook, and this is what a Jupyter notebook looks like in VS Code, and it works just the same as any Jupyter notebook. You know, the other place that I want to show you a Jupyter notebook is in Google Colabs. So I know we showed you this once before, but I just want to show you again. So this is collabresearch.google.com, and I'll just make a new notebook. And it takes a little bit to spin up sometimes. So there are two kinds of code cells here, or two types of cells here. There's a code cell and a text cell. This text cell is Markdown. So, oops. This is Markdown, and if I run it, notice this is what it looks like. It previews the Markdown over here. And if I run it, it renders the Markdown directly. So everything that I just did in the Markdown file, an actual Markdown file, I can do here. You know, I can make a, you know, print, hey, right? This is not a runnable cell here. This is actually a Python Markdown cell within a Markdown cell in Jupyter Notebooks. Whereas these are code cells, right? This is print, hey, and that'll just print, hey. So that's another reason to use Markdown. When you encounter Jupyter Notebooks, or when you're using Jupyter Notebooks for, say, exploratory data analysis or something like that, this is going to be, it's going to be really helpful for you to be able to, you know, annotate things as you go. Without, you know, because you can always use comments, right? You can always write comments. but comments are just a little less readable than an actual Markdown cell, right? You don't get headers, you don't get bold text, which I didn't show, but you know, I can. So this is bold, right? You can have italic text and everything like that. So so that's what connects Markdown to Jupyter. The other thing about Jupyter, especially about these Google Colabs, you can allocate GPU time to a Jupyter notebook, which means that if you're training, let's say you want to train a neural network like a convolutional neural net on a massive image data set, and if you do that on your computer, it's going to take 4 or 5 days. You can, if depending on what you allocate to it, the GPU you allocate it, to on Google Colabs, you might be looking at 20 minutes to an hour of paid time on there, which is a drop in the bucket and doesn't lock your computer up for a few days. So this is kind of it's a really nice place to go test things, to go see if something will work. And it's very low cost. Okay. So let's think about a kind of a basis for understanding machine learning. And for that, I think I'm gonna do a little bit of drawing. So we've been programming, and in our programming process, we've been doing this thing where we look at a problem, right? So we've got some problem, and we code a solution. Okay, so we go ahead and we code a solution. We're writing the procedure, right? We create a procedure to solve a problem. So let's think about this in terms of let's think about squaring a number. So we can write a procedure to square a number. And maybe that looks like I don't know. It just looks like this, right? N squared. Well, that's really simple. That's a very simple procedure to write. This function, the square function, if we're thinking about it as a function, we know how to do this, right? It's a known algorithm, and for that reason, this is a very reasonable way to go forward with that. So if we were to take this and think about it in terms of machine learning, well, maybe we have a data set of squared numbers, right? So this is procedural, and this is machine learning. Just put a line between these. And so if we're thinking about this as we're going to change the way we approach solving a problem, right? So in machine learning, in general, we'll have a data set of inputs and outputs. And maybe that looks like for our squared problem here, it's like, well, we've got 2 and 4. And then, can I do this in my head really quick? 24 and 20 times 28. Oh, shoot. I have like a fast squaring algorithm that if I'm not on the spot, I can totally square numbers really fast. But what did I say? 24 squared? Okay, 576. So 24 is 576. And let's say we've got, I don't know, maybe we've got n samples of this. Well, if we have enough data, we can take our input and pass it into a machine learning model. The machine learning model takes a guess, right? And then we compare the guess to the actual outcome. And this comparison, right? This comparison is going to go back around and inform the machine learning model, right? And so we can just adjust here. And then there's going to be a certain point where our machine learning model is either finished or we reach some threshold, right? And what we get out of this is a trained model, right? We have a trained model that can then take some input and square it, right? It'll give us the square of that input. Now, it may get it a little wrong sometimes, and that has to be okay for our problem, right? For squaring a number that really often won't be okay. But, you know, if it's a much more complex function, right? What if it's a very complex function? Then what we're really doing here, and I think I mentioned this before, what we're really doing if it's a more complex function is we are considering a sample space of all, let's say all known, not all known, all functions. And what our machine learning model is able to do, it's able to discern a subset of functions from which it'll choose a function that works well enough. Okay? Doesn't mean it's the only function that would work, right? In fact, there are infinitely many functions that will work within a within a certain threshold on a given phenomenon. But what we're going to see is that one algorithm might give us this function that will reasonably solve our problem. Another algorithm, or maybe the same algorithm with different tunings, will give us this one. And then maybe another algorithm would give us a function out here that maybe doesn't work, but is the function that it comes up with to try to solve the problem, but still it doesn't work. And either we didn't tune it well, or our data, we don't have enough data, or it's not an appropriate machine learning algorithm to solve that problem. So really at the end of the day, we have some data, we have some pool of data, and in most cases, I don't want to say most cases, but in a lot of cases, we're going to have some input and we're going to have some target. And our input and our target are used to train a given model. And what we get out of that is a trained model that can make predictions on new and unseen data, right? So here's our trained model. Here's our unseen data. And what our goal is reasonable predictions. So this isn't all of machine learning. Not all of machine learning is exactly like this, but there is a subset of machine learning called supervised learning. And this is when we have, when our data has some input vector, right? Some input. and a target. So, just to be simple about it, let's say we only have two branches of machine learning. We've got supervised, and then unsupervised is the other one. And unsupervised is only a little, well, it's a bit different. In this case, let's say we've got some pool of data, and maybe I'll represent this in a scatter plot. So, unsupervised. Let's say we don't have a target, right? And we just have a bunch of data. We just have a bunch of non-differentiated data. And, if I did a couple different colors, we could see a couple different classes of data. But let's just say we have non-differentiated data. And we might have two features here, X and Y, but neither of these is the target. Neither of these are things we're trying to predict. So if that's the case, what we might try to do, and this might make more sense if let's say we also have a Z dimension here, right? We've got three features that we're thinking about. We've got X, Y, and Z, right? So if we're thinking about this, there's going to be more or less similarity between different data points. And what we might start trying to do is create groups, like maybe this is a group, and maybe this is a group, and this is maybe another group, and this is another group. And then what we might decide here is that, oh, well, maybe there are 4 categories here. And does it make sense that there's 4 categories? If there are, if it does make sense that there are 4 categories, well, we can use that. We can use that in our business problems. So, are those the best categories? We don't know. We have to qualify that. We have some rigorous ways, and we have some ways where we just look at it. Right? We often just look at the categories and we ask, as a human, does this make sense? Right? That's often the best way to qualify the results of an unsupervised learning algorithm. Yeah. Searching a haystack without a needle. I think that's a really good way to think about it. One of the major areas where unsupervised learning models really are very applicable is in marketing. So if you have a bunch of customer profiles, right, and you have a history of the things they've bought, then and that's really, let's say that's all you know about them, then you can make categories of people based on the things that they bought, right? And maybe you figure into there some region as well, right? And what you start having here is like a idea of customer profiles. You can use machine learning to do this. Classically, marketing doesn't use machine learning to do this stuff, but anymore, if you are in marketing and you're not using machine learning, you're kind of not doing marketing anymore, because machines can, like, let's say there's this model called LDA that is very dear to me. I've done a lot with it. It's a latent Dirichlet allocation, and you can take a massive corpus. Let's say you take 20,000 books. You can put this through LDA, and let's say LDA, and you decide, well, I think there's 30 topics across. I think there's 30 topics. Let's just say that. What do I mean by a topic? Well, it's some kind of latent signal that isn't really defined, but we're going to think of a topic as being defined by important words to that topic. And let's say you process this LDA with 30 topics, then you get, let's talk about book 1 from LDA. Book 1 is going to be represented in terms of being a mixture of those 30 topics. And, I don't want to write a massive list here, so let's just say there are, 4 topics. So topic 1 maybe book 1 is 0.25 of topic 1, and 0.1 of topic 2, and 0.15 of topic 3, and 0.5 of topic 4. So if you know this about book 1, and you have some other measurements, some other mixture for book 973, you can quantify the similarity in terms of those topics, right? So let's, instead of thinking about books, let's think about people. Let's think about people and what they write on social media. And any person is represented by every tweet, every Facebook post that you've been able to collect from them. I think you're going to be able to start describing people in terms of describing the kinds of things people write and the kind of presence they have on the internet based on the topics that are prevalent in their social media output, right? And you can compare users at that point. And you can say, well, this user is more similar to this user, and maybe you can start, creating these categories of users based on these distributions of topics. We could change this to a distribution of interests, right? We can change this in a lot of ways. We can change it to a distribution of the descriptions of items that they've purchased. So all of these things, Cambridge Analytica. The thing is, this is not hard to do. This is really not hard to do. Here's the thing about it. You can take this even further, and you can look at the seeds of influence. You can say, okay, well, I'm seeing this talking point, come up a lot in this social network. Now, this talking point, where did it originate? And you can find the originators of various talking points. And that becomes a very powerful tool to, it can be a very manipulative tool. It can also out propaganda machines. And, there's a lot of ways, right? The technology itself isn't necessarily evil, but it can be used in very evil ways. That brings up a whole other thing in terms of ethics that I'm not going to talk about here. I'm very happy to talk about stuff like that one-on-one. If you have interests, especially in natural language processing, for tracking things down, for discerning social patterns, that's something I play around with quite a lot. So if you have any interest in that regard, definitely hit me up. Okay. So hopefully that gives kind of a reasonable basis for what machine learning is. And I'll just reiterate this in terms of supervised and unsupervised models. Do you have a target variable in your data? Are you trying to predict housing prices? Are you trying to predict whether or not someone's going to buy something? If you do, it's probably a supervised model. If you don't, if you just have a pool of data, then you're probably going to apply an unsupervised model from which you're going to try to discern a signal, right? Is there a signal in there? Can you decide that there is a category of individual or of item? So just small list of examples of supervised and unsupervised problems. So a supervised problem could be predicting miles per gallon based on descriptors of a vehicle, like, I don't know much about cars, so I'm not going to embarrass myself. But, we can take a bunch of measurements of aspects, engine block size, I don't know, size of a differential, whatever, maybe we're talking about specific vehicles. And you can predict miles per gallon. And you can probably come up with a really good model to do that based on the cars that are already out there in the world. So predicting customer churn based on prior churn data and customer behavior. So, is your customer going to leave your cell phone carrier, right? You want them to persist there, right? And you're trying to make predictions so that you can offer customers some kind of deal. You reach out to them preemptively before they leave, and then they stay with your company longer. Tagging images based on prior tagged image data set, right? You've got 100,000 images, and every item in the image is tagged. So you train a convolutional neural net, and you pass in new data, some image of that you take randomly, and the model will probably do a really good job of tagging all the objects in that image. There are actual public data sets that are very helpful if you have that kind of problem in mind. And then unsupervised problems, as I said, describing customers based on buying choices, document topics based on word frequencies, which I kind of talked about. Grouping similar images together based on morphology. It's totally something you can do. You can gather different, using a convolutional neural net, you can gather, like different patterns that are emergent across a bunch of images. And you can look at the frequency of those patterns, and you can compare them so that you start grouping images together. And let's say you have pandas, dogs, and cats. You can have an unsupervised approach that will differentiate those pretty effectively. Maybe it won't do as well for some cats or some dogs, right? Or some pandas, I guess. But, it's going to probably do a really good job depending on how you build that algorithm. And that would be an unsupervised kind of problem. Okay, so I'm just going to drag this comic up here. So when we're thinking about machine learning, a nice place to start is with a simple scatter plot. And that scatter plot, we have a simple scatter plot here, right? We've got an x-axis, a y-axis, and we're trying to find a signal in the data. What we can see here in this is from XKCD, by the way. So what we can see here is that, we can draw this line through this data, and hey, it looks reasonably okay, right? But, it kind of looks reasonably okay to draw a curve through it, or a logarithmic curve, or an exponential curve, or some Loess curves, right? All of these look like they could be signals in the data. And it turns out that, maybe this data doesn't have a discernible signal with this model. And so this is something that we run into quite a bit, where we cannot just draw a line through some data, or draw like a multidimensional manifold through some more complex data. We can't just do that. We have to qualify that our machine learning algorithm is doing what we want it to do. And that I'm going to try to build some intuition around that. So the way that we generally do that with supervised learning models, and not that there aren't ways to validate unsupervised models, but the way that we generally do this with supervised models is through a process called cross-validation. And really, our goal with a supervised model is to make predictions on data that hasn't been seen before, right? The model has never seen this data before, and we want it to do reasonably okay. So we set a threshold, a performance threshold, and we say, okay, we want to meet that performance threshold. So the way that we can validate our data is that we split our data set into, let's say, 80% and 20%. We train our model on 80% of the data, and we validate it on 20% of the data. In general, we actually use three sets of data. We use a training, validation, and test. So training, we validate our model, and then after we validate our model, we find these optimal settings for the model, settings that we call hyperparameters, and then we take those optimal settings and we train the model a final time. Maybe we add back in our validation data so that we get a slightly better trained model, likely a better trained model. And then we've got this other holdout set, a test set, that we use to report our final metrics. When we do cross-validation here, I'm just going to use a training set and a test set, and I'll show you that. You don't necessarily need to have a three-way split. I think often a three-way split is best in production, but if you're just proofing something, a two-way split is totally fine. So we call this cross-validation, and the splitting we call a train test split, right? Train test split. So why do we do this cross-validation, right? You always want to validate the effectiveness of your model, right? It's science, and you want to be able to, when you're looking at that curve and you're saying, oh, that curve looks like it's okay, you want to be able to falsify your claim that curve is okay. You want to be able to say, no, that isn't actually doing anything. I'm just training on noise. That's something you want to be able to do. And if you can't do that, then it's not really science, right? So we use CrossVal as a way to validate the effectiveness of models. I said this before, unsupervised validation, you discern these signals. The unsupervised validation, a lot of the time, looks like putting eyes on it. Although there are some automated methods. With latent Dirichlet allocation, LDA, that I mentioned before, you put your eyes on it. That is the way that is recommended. I came up with a naive way to, with dimensional projections to, try to optimize for a value of topics, like n topics, which is better, 5 topics or 20 topics, right? I found a way to do that, but it wasn't, it's like it's still theoretical. Everything in that domain in terms of validation is fairly theoretical, as opposed to supervised learning, which, you can always apply CrossVal, or you should always apply CrossVal. And there are more sophisticated forms of cross-validation. There's one called k-fold cross-validation, where, you have your data set. Let's say this is your data. You actually split it randomly, let's say, into 5 folds. So with a k equals 5. And then you train on this, test on this, and then you train on this, and test on this. And then you train, and so on. So you train on all these different, permutations of your folds, 1, 2, 3, 4, 5. And then you look at the outcomes of that, as opposed to what we're going to do today, which is just, we've got this data set. We're going to train on this and validate on this. Okay. So I'm going to start working in this Jupyter notebook, and I'll try to remember to hit save, but I think this should save fairly... Oh, no, it's not going to save automatically. If you run Jupyter Notebook in the browser, it does save automatically. But, this is not going to do that, so that's fine. All right. So the first thing, I'm just going to put a little markdown cell that says, CrossVal intuition. And the first thing, maybe I'll do this above that. The first thing I'll do is I'm going to suppress warnings because I'm going to be using a couple things that are in the process of being deprecated. But I'm using them because I want to keep this very simple. So I don't want to throw any warnings, so I'm just suppressing warnings. Okay. So we're going to build a scatter plot. And I'm going to build this scatter plot using a simple polynomial. All right. So here's some polynomial, ax to the fourth plus bx cubed plus cx squared plus dx plus c. I'm going to write a function that is going to deliver us different levels of complexity of data. And then we're going to apply to that, kind of a boxed linear regression, a boxed machine learning model that's going to draw a line or curve through that. So we're going to define the phenomenon that creates our data. And then we're going to take a machine learning model that is going to draw a line through that data based on the complexity that we inform it, right? So offhand, if I do a sort of order 4 polynomial, what that might mean is that I have up to 3 curves in my data. But if I do an order 1 linear regression, right? If I tell my linear regression, well, this is a linear fit, a fully linear fit. What that's going to do is it's just going to draw a line through our data, regardless of the curvature that's there. So how do we do this? How are we gonna write this? I'm going to use a library called NumPy. I'm not sure if many of you have seen NumPy as yet, but how do I say this? NumPy is so amazing. Your computation time with lists is awful, and you don't know it. When you start working with larger amounts of data, NumPy is what you're going to use almost all the time. You're going to actually move quite a bit away from lists and dictionaries, and you're going to use NumPy arrays, and you're going to use pandas data frames instead. But they do act a lot like lists and a lot like dictionary, and pandas data frames do act a lot like dictionaries. So, it's important to have those simpler data types before, very solidly understood before you move into NumPy arrays and pandas data frames. But I'm going to be using NumPy here, and I'll do my best to talk through anything that doesn't look list-like. But you can think about them as being really great lists. And then I'm going to import matplotlib pyplot. This is going to be my my visualization library. So I'm going to plot a few things as we go. And let me look at Slack really quick. Do you take the CrossVal data, test data, and train data from the same data set? Yes. Yeah, in general, you do. So let's say you get 10,000 rows of data. You might train your model on 8,000 rows and validate and, let's say validate on 1,000 rows and then test on 1,000 rows at the end of everything. So yeah, generally you want to pool that from the same data, but you also want your data to be representative, and that's again one of those huge challenges in data science and machine learning, having actual representative data that isn't polluted by your sampling process. It's very easy actually to pollute your data with your sampling process. What is the proper proportion of each type of data to get a valid model without overfitting? It depends on the machine learning algorithm. In general, I think about it less in terms of the proportions than in the number of rows that you might need, right? So here we're going to have, when we get to it, for K and N, we're going to need, 100 rows of data is totally going to be enough. A lot of the time with, let's say, a convolutional neural net and, facial recognition, you might end up training on hundreds of thousands of images, and your holdout set might be, 10,000 images, maybe more, maybe a lot more. But it really depends. Often, the classic is a 70-30 or 80-20 split, but with neural nets, often the split is more like 10% or 5% because we have such large data sets that we train with. But it really depends. Yeah, it really depends on the algorithm. Also, we're likely going to get, we're probably not going to finish this lecture today. We'll wrap it up on Monday. So we're going to get as far as we get, and then we'll finish up on Monday, and then we'll have the rest of the TI technical interview lecture in the remainder of Monday's class. Okay, so I'm importing NumPy and Matplotlib, and I'm going to just define a function really quick that is going to plot some stuff. I'm going to, plot this, plot some generated data where I insert some noise as well. Okay. So I'll call this plot scatter fit, and I'm going to put in a number of samples, right? How many points are we going to draw? Let's say 50 by default. And what is the complexity of the function that creates our data? Well, let's make it just a simple linear function first. And, I'm sorry. Fit complexity is actually the complexity of the model that is going to fit our data. And here I'm going to have degree, which is going to be the complexity of the function that creates the data in the first place. So just going to break n out. So I'm just going to use n for our number of samples. I don't actually have to do this because I'm not modifying n, but I often do this just in terms of my own naming of things. So I'm going to set a random seed. And what this means is when I generate random values, I'm always going to generate them in the same way. In general, you don't want to do this for anything that's in production. If you're using something truly random, you don't want to do this. But for our purposes here, I'm going to generate this always in the same pattern. And now I'm going to generate some random x values. So NumPy has its own random module, so I'm going to use that. I'm going to use .rand, and this is going to get me a list, essentially a list, not actually a list, it's an array. It's going to get me a vector. Well, okay, it's actually an array in NumPy, but I'm going to call it a vector because that's more mathematically appropriate. It's going to get me a vector of n random numbers. So x is now a vector of n random numbers. And I'm going to, now I'm going to just define y. So y is going to be the result of x values passed through some function, right? So how that looks, so I'm going to just define polynomials. What that looks like is if the degree of our function is 1, right? If it's a linear function, then I'm going to call this 5x plus 3, right? And now I'll say if we're generating from, if we want to generate from an order 2 polynomial, then I'm actually just gonna take this and continue to adapt it. So I'll say this is 3x squared, and can continue doing that. Oops. So if the degree is 3, then maybe it's negative 0.2 x to the third, and then if it's 4, then let's notice my coefficients are getting smaller and smaller. I'm doing that for a reason, because I don't want my I don't want to disappear the relevance of my lower order factors here. So I'm just decreasing my coefficient. So x to the fourth. Okay, so these are my functions. Or my functions for different degrees of the polynomial that we can set up here. So that's going to be what generates our data. Okay. Now, we're going to get a range of values. So what is the range of y? I can use that. I can use this PTP function from NumPy to get that, and I'm going to call this yval range, and I'm going to use it shortly. So I'm going to add some noise to our outputs, right? Because if we think about the function that is going to create this, let's say it's a linear function, every point is going to be on this line, right? But we want to create points that are offset from this line, right? And I'm going to do that randomly. I'm going to do that randomly based on the normal distribution. So what you might imagine here is that the distance is going to be like this. We're more likely to be closer to the line and less likely to be further away, right? So the density should be close to this function and get more spread out as we get away from it. Okay, so I'll add normal noise, and I'm going to do this in a sort of, well, for every point, I'm going to add some random normal noise, and that's going to be centered around, from 0, right? And then scaled. I'll do 1 divided by 10. And so as our y values increase, the scale of this noise is going to increase. Oh, it's not actually a full comprehension for each point in y. So notice I'm overriding y with y that has noise added to it. Okay. So at this point, I'm going to define essentially our machine learning model, but this is just going to draw a line for us. This is going to be another thing from NumPy, and it's going to be a very basic regression line. So I'm going to set a fit complexity, I'm just copying our fit complexity variable and using it like that. And then there's this poly1d. This is just a very simple linear regression that is going to draw a line in our data when we get to it. So np.polyfit x, y, I'm passing in x and y, and I'm passing in the fit complexity, right, which is going to be the order of the polynomial that is discerned by this poly1d. Not pol1d, but poly1d. Let's see, poly1d, np polyfit. Okay. And then there's a chance that we have duplicate values of x. We don't need them, so I'm just going to get rid of them like that. Okay. And at this point, we can actually just plot this, and whenever you plot something, whenever you make a plot, make sure you annotate it. It's profoundly important. Let me say that. It's profoundly important that you annotate your plots. It really is. And, even if you are just building something for yourself, no one else is ever going to look at it. I can tell you that if you don't annotate it, you are not going to know what's going on in 3 days when you look at it after you walked away from it. And that's like most code, right? You walk away from it, you come back to it, and you're like, I don't have any idea what I was doing here. And then it takes almost as long to read through it and figure it out sometimes as it did to write it. Okay. All right, so there's that, and so I'm going to annotate this with multiple lines. So I want to show n, right? How many samples are we taking? I want to show the degree of the data. And I'm not using f strings here. I think it's a little nicer. Well, I could just use f strings. I'll just use f strings. So since we've been using those almost the whole time. So our data degree, this is just going to be degree. And then this is going to be, then we want to consider also our fit complexity. So fit complexity, which, yeah, just called fit complexity. And I think that's it. Hopefully there isn't a typo in there or something, but I think that's actually good. Okay. And then at this point, we can just plot. There's a very simple way to plot a scatter plot, and it's just this. I'm going to pass in my x values and my y values. I'm going to set a color. I'll just set it to yellow right here. And then I'll set our alpha. This is just going to make it look a little nicer. And then I can plot it, plt.plot. And I'm going to plot the, I can plot our line, our regression line, x against regression, okay? Okay, so at the end of all this, you do plt.show. And yeah, and then we can just call this. Let's call it with the default values. Hopefully this is not broken. It's very possibly, oh, no, there we go. Okay, so we have some data and we drew a line through it. Cool, that's the goal for this function. This line looks like it fits that data pretty reasonably. What happens if we change this to 10 samples, right? We're only going to generate 10 samples. It may not be obvious, but this has a different slope, right? So let me do this. I'll just snag this. And I'll run this again with 50 samples. And we can see, well, let me just get this all on the same page, I guess. Here we go. We can see that there is a very slightly different slope. We still have a decently representative line, and this is just, us, it's just getting at the more data you have, the better, right? Pretty much that's going to be universally true. It's very rare that having too much data is going to be a problem, except in terms maybe of storage. So what if we change the complexity of our regression? Like, what if I change this to, let's say, an order 10? At this point, we are what you would call overfitting the data. And, what that kind of looks like for us is we are connecting the dots. We are connecting these random dots. We are following a signal that is not, well, we're following the variation and not the underlying signal. So if we're generating data from, if our phenomenon has an order 1 polynomial, it should be, I think it's a little obvious, but we probably would want a fit complexity that looks more like 1, right? Now, what if we are generating data with an order 4, let's say an order 3 polynomial? Now we're just cutting a line through something that's obviously more complex than that, right? There's more curvature here than what this model can handle. And part of what's happening is, well, we can think of our model as being very opinionated here, right? It has a very strong opinion about what's happening. It's getting it very wrong because it has that strong opinion. That's bias, right? So we have a high bias model, whereas before, when we were connecting the dots, we were following the variation in the data, not the signal that created the data, and we call that high variance. So we want to temper the bias of our model. And actually, fit complexity of 2 seems to do pretty well here, given the data that we can see. Now, maybe if we had 500, we would see this fail a little bit. And we do. There's a little bit of, we kind of lose homoscedasticity, like we lose even distribution around our model fit. So, we lose it a little bit here, we lose it maybe a little bit out here, it's hard to tell. And then something's happening down here, but it's unclear. So let's change this to an order 4 polynomial that's generating the data. This actually does really well. And this kind of brings up a subtler point in this space. There is a simpler model. Like our model is simpler than the function that created the data that the model is modeling, right? But it's doing pretty well, and maybe it's doing good enough. And this kind of brings up, one of those things, one of those, I don't want to call it a rule of thumb. Well, maybe I do. Maybe I do want to call it a rule of thumb. Well, we're using the concept of Occam's razor. We have a simpler model that effectively explains the signal in our data. And even though it's not the actual underlying function, keep in mind that we shouldn't know in general the actual underlying function. If we do, we would just code a procedure to solve the problem, right? But we don't know. We don't know that it's a order 4 polynomial generating this data, but it looks like we can fit it with an order 2 polynomial, an order 2 regression. So we can maybe just choose an order 2 regression here and be good with that. Are we going to see, this is all intuition because we haven't rigorously qualified this or anything, but do we see any significant improvement with an order 3 fit? Not very discernible, right? Maybe there is. And we could qualify that, and then we would ask, well, is the computation time worth it? Is the explainability of an order 2 fit, which an order 2 is going to be more explainable than, let's say, order 3, right? We've got 2 factors that are generating this response, right? This Y output, this Y outcome. That might be simpler than, and more, and better for the people you need to explain this to than having a much more complex fit. So here's something. If we have this degree 4 polynomial and we try to fit it with a fit complexity of 20 with this many samples, it's still kind of doing okay. And what if we have 5,000 samples? It's kind of doing just fine, right? And I think this is another caveat. If you have more data, you can tend to use more sophisticated models, and use more sophisticated settings within those models. We're not overfitting on 5,000 samples. However, if we had 50 samples, we've got a mess, right? This is just connecting the dots. Okay, let's take a 5-minute break, and we'll get as far as we can in the machine learning workflow for today. I think we'll get through a good part of it. We might get to a good stopping point, and maybe we'll stop 5 minutes or 10 minutes early, just so that it balances out nice in the next class. But I'll see y'all back here in 5 minutes. Hey.
One minute remaining.
I'm totally down. I'm planning on just working on loop all day tomorrow. Yeah. Yeah, do you want to just, you can order it, do you want to just order the Cosine Similarity for me and, yeah. Cosine and, sure, yeah, Tom Cow would be good too. Yeah. Okay, so So this is kind of the intuition to inform our cross-validation. From here, we're going to get into, more generally into a real problem. So, sorry, give me 1 second. Okay. So we're going to apply cross-validation to a simple classification problem. There's this data set called the Iris data set. It is a toy data set. There are a bunch of different toy data sets. There's one called cars. There's one called house prices. There's a bunch of them. And we're going to be using the Iris data set. It's very simple. In fact, I can show it to you in just a second. We're going to apply KNN, which is k nearest neighbors. I'll try to make a justification for why k nearest neighbors works, why it does anything. And then I'm going to be using a simplified version of CrossVal. We're not going to have a validation set. We're just going to have the training set and a test set, which is a fairly normal way to prototype things anyway. So I didn't want to complexify it with like, oh, let's split this out a bunch of times. Yeah, let's start talking about this. So k nearest neighbors is a supervised algorithm, and maybe I'll start drawing this out a little bit. So k nearest neighbors is supervised. It's one of our naive algorithms, and all I mean by that, that doesn't mean it's not effective. In fact, it can be very effective depending on the data. But it's naive because it can give us a benchmark for more sophisticated algorithms. So KNN, logistic regression, linear regression, decision tree. There's a number of kind of simple algorithms that have more, I'll just say they have more complex versions of them in some cases, or they just, we use them as some kind of benchmark. We say, okay, well, if we have a neural net and it doesn't do any better than a linear regression, well, we might want to be cool and awesome and say, hey, I used a neural net to do this. But if it's not doing anything better than a linear regression, then use a linear regression. You want to use, again, this is the other facet of Occam's razor. You want to use the simpler model that is as effective as a more complex model. So KNN it's supervised. There's X and Y data, right? That's what we mean by that. Something interesting about KNN that's different from the prior model that I applied is that it's non-parametric. And that actually means that there are types of data that we can use KNN upon, and it's going to be able to, and it's going to work maybe better than regressions that we might use, or classifiers, let's say, that we might use. So, by non-parametric, we're not really considering lines here. We're not considering, some kind of matrix reduction that allows us to draw a line through a scatter plot. We're using kind of a very different approach, and I think KNN is really cool because it has this interesting algorithmic feel, and it's very intuitive. So, what else? The training data, here's another thing about it. The training data is essentially the model in KNN, and I'll explain why that is in a second. But this can lead to some weirdnesses, like you actually have to store the KNN model, which is the data, in memory, which can lead to a prediction of category. Let's say, if we're thinking cat versus dog. Let me explain this a little bit. So let's say we have a bunch of cats and dogs, and do cats as green. So cat, 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 and then there's a cat over here. Maybe there's a cat over here. It seems unlikely. And let's say our features are weight and height. So we've got a very tall cat right here. It doesn't weigh as much. And we've got, kind of a big cat out here. And then we've got dogs that are, we've got a dog down here. Then we've got, more dogs over here. They tend to be taller and heavier, right? So if we're trying to draw a boundary between these, and mind you, this is before what we were looking at was a regression problem, because we're sort of trying to predict a continuous outcome. In this case, we've got a classification problem, right? This is classification, because we're trying to draw some kind of decision boundary. So if we were doing something linear, maybe our decision boundary would look something like, maybe it would be like that. And anything that's over here, right, is going to be, we're just going to predict as a cat. And we're going to do pretty well, right? There's only one dog and two cats over here. So we're going to do pretty well in predicting in this way. So what K and N does is a little bit different. We're not drawing this kind of linear decision boundary in that way. We're considering our decisions in a very, in kind of a very different way. Our prediction is going to be based on a majority vote of the most similar neighbors. So if we set K equals 2, and we look at this item right here, well, that item is a cat. We're going to look at its neighbors, which are cat and cat. Its two closest neighbors are cat and cat, and we're going to say, oh, well, that's probably a cat. Okay, then we look at this one, and we say, oh, well, its two closest neighbors are cat and cat. Well, that one's a cat. We look at this one, and we say, okay, well, its two closest neighbors are cat and dog. Which one's closer? And then we're probably going to predict dog on this if we have a K of 2. So we're going to get that one wrong. We're going to look at this one, which is a dog, and we're going to take a vote, cat and cat. Okay, well, we're going to get that wrong because the closest thing is, the closest two things are cats. So we're going to vote cat. And then we look at this one. This one, it looks like cat is closer. We're going to get that one right. We're going to get this one right. We're going to get this one right. This one we're definitely going to get wrong. We're going to get that cat wrong because the two closest things look like dogs. In this case, we're probably going to get this wrong because the closest thing is a cat. We're going to get that wrong. We're going to get that wrong, obviously. But, with a K of 2, we're still doing okay, right? We're getting 1, 2, 3, 4, 5 wrong out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We're getting roughly 5. We're getting about 75% correct. We're guessing 75% correct here. That's not that bad. Considering we don't have much data, considering this is the way that these are the features we have, height and weight. So, this is one of those algorithms that if you sit down and think about it, you can program this yourself. And I really like that aspect of it too. And in the future, I'm probably going to explicitly turn this into a 2-day class so that we can code through this, end to end. Just because I think it's a fun algorithm. It gets you kind of primed in the idea of, oh, I can actually write these things. I can actually solve these things. This and logistic regression is along the same lines. So given a structured data set, we set a value of K, right? That's where we said K equals 2. And then for each data point, we find the K most similar data points, which we did. We looked at the two closest neighbors. We checked the class of each neighbor, each of the K similar data points. And, so two cats, well, that's a cat. A cat and a dog, well, is the dog closer? It's probably a dog, except we got it wrong. Then we assume the current data point is is of the majority class checked. Okay, so hopefully that's pretty simple. If you have any questions about what that algorithm is doing, definitely ask. I think this is a really nice algorithm, and it's really friendly and doesn't feel particularly mathy, but still very algorithmic. So how do we define distance? This is just a little aside. Turns out that there's a lot of different kinds of distance and similarity. And the way that I think the way that we're probably thinking about it here, in this case, is something like Euclidean distance, where if we're considering Euclidean distance, we're going to, if we just think about this like a plot, then we have 2 points on that plot. We have a point here and a point here. And if we want to decide what is... I don't know, my pen is being weird. All right, let's try that again. Okay, it's just drawing on its own. Okay, well, I guess I'll be really careful about it. Euclidean distance here is just that blue line. And that is, the distance of that line is, it's as the crow flies, right? That's how we think of Euclidean distance. Now, the way that we're going to think about, there's this idea of Manhattan distance. If you think about walking around in Manhattan, you can't walk through a building to get somewhere, right? So what you're going to have to do is, you walk a block, a city block, and you walk another city block. Okay, so that's, regarding the idea of Euclidean distance versus Manhattan distance. That's 2 different distance metrics, and one might be more appropriate for your data than the other one. So let's think about this idea of cosine similarity. Let's say you have a vector, and we haven't really talked about vectors, but let's say you have a vector. If you have a vector, there are going to be times where there's some other vector that you want to consider in relation to it, right? And, well, maybe there's this vector, and it's a little bit, it's a little bit longer. It's a slightly greater displacement, but we can measure the angle difference here between the two, right? We can measure that, and then we can compare it to another vector here. And we can see that the angle difference here is larger. So this, this sort of fuchsia one is more similar to our home vector than this lighter blue one out here. So that's kind of the idea of cosine similarity. And there's a bunch of other metrics, distance metrics and similarity metrics. I won't get into Hamming distance here. It's really cool, but it's also, deserves a couple classes in and of itself, and you probably won't use it anytime soon. But yeah, I just want to bring this up, that there are a lot of different ways to quantify similarity and distance. Okay. I think we'll probably be able to get through the first part of our actual workflow. So we're gonna start off with the most time-consuming part of a machine learning workflow, which is your EDA. We call that exploratory data analysis. When you get some data for the first time and you don't really know what's going on there, it's going to take you a long time to look at it and to learn what's happening. Before you even do any machine learning on it, you're going to explore it. You're going to quantify. You're going to measure things. You're going to try to explain things on your own. You're going to build hypotheses, and there's a lot of cleaning that happens with data. In fact, so much cleaning. We're not doing any cleaning here, okay? But there is so much cleaning that has to happen in almost any data set. It's amazing. You have institutions that curate data all day, right? That's what they do. And there are massive anomalies in there that you have to explain to yourself when you encounter them. And they will mess up your machine learning model. They'll mess up your measurements in general. happens all the time. And so in this process, you find anomaly detection as well, or you apply anomaly detection as well. There's just a lot going on when in the cleaning stage of the data. And then there's also reshaping the data. And all that really means is, what do you do to the data to make it able to be used by a machine learning algorithm? What do you do to it? And, we're going to do some very simple, we're going to do something very simple in this regard. There's something I'm going to call cleaning that's not really cleaning. This data set is already cleaned and curated because it's, a very old toy data set. Okay, so let's do this. And I'm just going to call this ML workflow. And part 1 is we're just going to import, clean, and reshape the data. So there's this cool thing. If you're on a Unix or Linux-based machine, there's this cool thing that you can do where you have magic commands, what are called magic commands, in a Jupyter Notebook. So if I type ls, these are actually the files in the folder that my notebook is in. If I want to, so I'm looking at these and I've got, data right here. The data set is in that data directory. So if I do ls data, then I can see the name of the data directory. The name of the file. Although I don't, okay, there we go. So iris.data.txt. Okay. So that's the name of the file that we're going to import. So I'm going to load a library called pandas, and there was a minor homework assignment, optional homework assignment to do a pandas tutorial. There's also pandas materials in our further studies. I think they've been fairly expanded at this point, and really, pandas is one of the most important skills when you hit the DSI in the first couple weeks. If you can get good at pandas before you get in the DSI, it makes everything so much easier, so much better. They're sort of like if spreadsheets were not awful, they'd be pandas, if that makes sense. So I'm going to import pandas as PD. This is a convention. That's usually what we name pandas when we import it. So import pandas as PD. Maybe I'll make this a little bit bigger for the moment. And if I look at our actual data, and maybe I'll do this in the terminal. So we can see that there's this iris.data.txt. If I look at the first number of lines of this, we can see that there are no names, there are no column names here, right? There's just numbers, and then the type of flower it is. And so in this case, what we would probably do if we just receive this data and it's a known data set, what we would probably have to do is go look up somewhere what is going on here. What does this data mean? You get data all the time that has no headers. That is much more common than you'd expect, and people will just pass that stuff around and they won't annotate it, like literally on the public site where they're sharing this data set. They're like, oh, you'll figure it out. It's a bunch of numbers, you have no idea what those are. And there are times where you're like, okay, I think the only thing I can do here is email somebody. And that's what you end up doing. You end up emailing somebody and saying, hey, do you have a description file for this data? Because I don't know what's going on here. And then they'll be like, oh yeah, here, and that's how you find out. In the worst case scenario, or actually worst case scenario is you don't hear anything back and you just build a model based on things that you don't actually understand, which you can sometimes do. And maybe that's okay. Not always, but maybe that's okay. Okay, so we're going to not look this up because I know what these are. So we're going to define the columns. I'm going to say columns and features interchangeably. The reason for that is if we think about it in sort of like a spreadsheet format, the features are in columns. Features are just the different types of variable, the different types of information we have about a specific item, right? So in this case, we've actually got 5 features. We've got, and these are all descriptors on the flowers that we're using or that we're studying. So this is going to be sepal length, sepal width, petal length, petal width, and the classification of the flower, which I'm just going to call class here. So I'm just going to make this list, and then when I import the data, I'm going to utilize this list. It's just going to make this a little bit easier when I read it in. So let's load the data. df, this is very common, just means data frame. And people will say, well, df flowers or something like that. I'm just going to call it df. That's very, very common. So there's this nice, very convenient function called read CSV. So if you have comma separated values, think about this. If you've been working with spreadsheets a lot and you have a bunch of spreadsheets, you can dump those out as CSVs. You can import them into pandas and play around with them, and learn pandas through that lens. So I'm going to import data slash is iris.data.text, and then there's no header in the data as I showed you. So I'm just going to say header none, and then we can name the columns by just passing in our names list above. Okay, so that should load the data, and let's just look at it. So df.head, if I do .head, that's going to look at the first 10 items in the data. And that renders kind of nicely in here because it's a Jupyter notebook. So this number on the left, this is just the index in pandas. Pandas defines its own index. And we can see the values, sepal length, sepal width, petal length, and petal width, and then the class that is these are all observations. That's another term, right? Feature, observation, variable, column. These are all interchangeable terms. So that's our first 10 items. Likewise, we can use .tail, right? Tail, we can do that. And that's going to get us the last 10 items. So it looks like we have 150 rows of data. That's not very much, but it's going to be more than enough for what we're going to do here. Okay, so something I'm going to do really quick, I'm going to set aside, even though I have these defined in that names variable, I just want to show you this because you're going to use it all the time. df.columns is going to give you a list of the columns. So I'm just going to do that really quick because we'll use that in a little bit. And if I want to see what this looks like, right, it's a list-like object. Sepal length, sepal width, petal width, and class. Something else to notice here, I didn't use a print statement, right? So Jupyter Notebooks will you don't need to use print statements if it's if the last statement that you make in the cell is, you don't need to use a print statement on the last statement in a cell. It'll just output it to your output here. If you don't want it to output, you can put a colon there. You can also use a print statement. That's absolutely fine. Notice it does render a little bit differently when you do that. So I'm going to leave that like that so it doesn't take up much space. And yeah, so at this point, we might start asking questions about the data. Like, well, I don't want to open up the file and look at everything. What are the different types of flower that we have in there? So what are the different flowers in? So I know that it's some different kinds of iris, but I don't know the names offhand. The way I can find that out is df.unique. So we have iris setosa, iris versicolor, and iris virginica. So we've got 3 targets that we're considering. Iris setosa, like these are the ones we're going to try to predict, these 3. Setosa, versicolor, and virginica. Okay, and then offhand, if I want to know how many rows are here, I can still use the len function, right? The length function. And even though a data frame is not a list or a dictionary or something like that, Python is really friendly about making it still work. Okay. So you can also do other things that are Python, like let's say for each row in the data frame, let's say the sepal width, I can iterate over this and look at each row. But I'm going to suggest that you try to not do this too much. It's better to do what we call filtering, but you can iterate over this if you're really stuck. So learn pandas the best that you can, but realize that you can still, for the most part, comparison gets a little weird, but you can still do most of the things that you can do in the base language with the data types you already know. So I'm just going to break it 0. And if I do this, we can look at the first 10 sepal widths that are in the data, like so. Okay. All right, so we don't have much time. So I think I'll just do one last thing here. And next time we'll plot the data and finish up the machine learning process. So I'll leave off here. I just want to show you, I want to separate our features that we're going to train with, right? Our X data, our big X data, from our little y data, right? Little y here is the target. It's a scalar value, right? We're trying to predict the sepal width, or sorry, we're trying to predict the class based on some variety of features. The features are a vector; they've got multiple items in them, whereas the target is just this single name, class, right? Versicolor, virginica, or setosa. So the way I'm going to do this is I'm going to take this data frame, and notice here that X is still a data frame, but it's going to be a subset of the columns from the data frame. So let's do, I'll actually just copy this from up here. I'm going to take all of these, except the class, right? This is our input, our X vector. So that's going to give us X. And then our target, we're going to call Y. And this is going to be the class. So let's stop here, because the next thing I would do is a massive comparison between the different features and how differentiable our classes are based on the features that are present. So we'll probably take the first 45 minutes or so, maybe up to the first hour in Monday's class, finishing up this. And then in the past, I've sort of defined, like as a group, we've kind of built something that looks like the interview, just running through the things that you might need to know. But I think what I'm going to do instead is build a mock interview and have it be a series of challenges that we do. I think that might actually serve you better, and I'll try to make it at the level of our actual technical interview, roughly at the same level, with some kinds of similar questions. And then that way, you'll have an immediate gauge of where you're at. So I'll try to allocate at least an hour for that. The interview, when you take the interview, it'll be you'll have a 45-minute, you'll have 45 minutes to complete it, essentially. And yeah, we can talk at more length about that, and I'll probably stay on for a lot more questions in regards to the interview after after class on Monday. So I'm gonna stay on right now for 5 to 15 minutes, depending on questions, and yeah, feel free to sign off. Thanks so much. We'll wrap up the machine learning materials on Monday. I think it's pretty fun. The plotting functions are fun, so I'll see y'all then. And oh, sorry, 1 second. Let me just stop recording.